Hi everyone. I would like to welcome all of you to today's class. In this class, we are going to discuss about two very important derivation. In the previous class, we learned about the first application of Gauss's law, that is electric intensity at a point due to an infinitely uniformly charged wire. So in this class, we are going to discuss about the second application, that is electric intensity at a point due to uniformly charged infinite plane sheet, and also electric intensity at a point due to uniformly charged spherical shell. And this is electric charge and electric field part 11. Okay, let's start today's class. So this is actually the second application of Gauss's law, that is electric intensity at a point, derivation of expression for electric intensity at a point due to uh, uniformly charged infinite plane sheet. Uniformly charged infinite plane sheet. Okay, first let us consider Cartesian coordinates. This is x-axis, one is y-axis, one is z-axis. X, Y, Z, those are Cartesian coordinates. Now we can consider plane sheet. This is plane sheet. Actually, that is placed. This is a uniformly charged plane sheet. It is placed in the YZ plane. This is a uniformly charged plane sheet. It is placed in a YZ plane. Now the electrons are removed from the plane sheet. What happens? The sheet actually gets positively charged. Sheet gets positively charged. Now we can choose two observation points. One is P and another one is P dash. Both are equidistant from the plane sheet. Okay, so the distance from P to O, this is R. Even the distance from O to P dash is also R. So after that, we can choose an imaginary Gaussian cylinder. This is an imaginary Gaussian cylinder. So taking P and P dash, that is the axis, P and P dash, that is the axis of the imaginary Gaussian cylinder. So this is the imaginary Gaussian cylinder. Okay. So this is a uniformly charged plane sheet. Actually, here y tends to infinity, even z also tends to infinity. This is a uniformly charged infinite plane sheet that is placed in yz plane. Okay, P and P dash, those are two observation points. Those points are equidistant from the plane sheet. So after that, we can choose what? The imaginary Gaussian cylinder, taking P and P dash. P and P dash, that is the axis of the imaginary Gaussian cylinder. So this Gaussian cylinder having three surfaces: a left flat circular surface, a right flat circular surface, and curved surface. First, let us draw the directions of normal and direction of electric intensity on each surface. Okay, what is the direction of normal at the left flat circular surface? So normal is always directed outwards. Normal means imaginary perpendicular to the given surface, directed outwards. So here A is uniform cross-sectional area of this Gaussian cylinder. So A vector is here outwards, directed outwards. And what is the direction of electric intensity at the point P? So let us consider a unit positive test charge plus Q naught that is placed at the observation point P. Due to this uniformly charged, positively charged plane sheet plus Q naught will experiences the repulsive force. That is also directed away from the plane sheet. Due to this uniformly charged sheet, plus Q naught will experiences the repulsive force. That is the direction of electric intensity at the observation point P. So after that, what is the direction of normal at point P dash? What is the direction of normal at the point P dash? So here is also the direction is away from this uniformly charged sheet. So this is a normal. Normal means imaginary perpendicular to the surface and directed outwards. So this is the direction of the normal. And what is the direction of electric intensity at this point? What is the direction of electric intensity at point P dash? A unit positive test charge plus Q naught is placed at the observation point P dash. Due to this positively charged sheet plus Q naught will experiences the repulsive force directed away from the sheet. And this is the direction of electric intensity. Okay. So after that, now we can choose a very small surface on the curved surface, that is ds. This is ds. So here ds vector is radially outwards. Ds vector is radially outwards. And what is the direction of electric intensity? So unit positive test charge plus Q naught is placed here. Due to this positively charged sheet plus Q naught will experiences the repulsive force. This is the direction of electric intensity. Okay. So after that, let us consider first the surface charge density of the sheet. Sigma is equal to Q divided by A. Sigma is equal to Q divided by A. So what amount of charge included by the Gaussian cylinder? The total charge, net charge included by the Gaussian cylinder is the net charge, net charge enclosed by the Gaussian cylinder. That is Q is equal to sigma into A. Now call this as equation number 1. Q is equal to sigma into A. So this is the net charge, total charge enclosed by the Gaussian cylinder. So after that, we have to calculate the total electric flux through the entire Gaussian cylinder. Actually, that is splits into 3 parts. One is electric flux through the left flat circular surface and electric flux through right flat circular surface and total electric flux through the curved surface. So the total electric flux through the entire Gaussian cylinder. So that is phi E. Phi E is the total electric flux through the entire Gaussian cylinder. So that is equal to flux linked with left flat circular surface plus the flux linked with a right flat circular surface, that is phi r, plus the flux linked with the curved surface, that is phi c. Flux linked with the curved surface, that is phi c. So phi e, that is equal to phi l, that is E vector. The flux is measured by taking the dot product of two vectors, electric field and the area. Area is A vector. So E vector dot A vector plus the flux linked with the right flat circular surface, that is E vector, that is also E vector dot A vector, and the curved surface, that is integration. Here we have to apply the integration. The integration of E vector dot ds vector, because here we are choosing just a small surface. So after that, remove the dot and vector sign. What is the meaning of dot product of two vectors? That is given by the product of magnitude of two vectors and the cosine of the angle in between that. So phi e, that is equal to phi is equal to here E A cos theta is the angle between E vector and A vector. Here the angle between E vector and A vector. This is A vector. So E vector, A vector, both are moving in the same direction. E vector, A vector, both are moving in the same direction. So what is the angle in between them? That is 0. So E cos 0 plus. So here is also E A cos, what is the value of theta? So on right flat circular surface, E vector is directed outwards, even A vector is also directed outwards. Both are moving in the same direction. What is the angle in between them? Again, that is equal to 0. So this is 0 degree plus integration of EDS. What is the angle between E vector and ds vector on curved surface? That is 90. EDS cos 90. So this term goes to 0 because cos 90 is 0. So after that, we will get the mathematical expression, that is phi e is equal to cos 0 is 1, cos 0 is 1. So EA plus EA, that is 2 EA. EA plus EA plus EA. Finally, we will get phi is equal to 2 times EA. This is the total electric flux through the entire Gaussian cylinder. Okay. Now call this as equation number 2. Right. So after that, let us apply the Gauss's law. According to the Gauss's law, the total electric flux through any closed surface, total electric flux through any closed surface, that is equal to 1 over epsilon naught times the net charge enclosed by the closed surface. The total electric flux through any closed surface is equal to 1 over epsilon naught times the net charge enclosed by the closed surface. And now call this as equation number 3. Okay. Now the equations 1 and 2 in equation number 3. So what is the value of phi? Phi is 2 times EA, that is equal to 1 divided by epsilon naught. What is the value of Q? That is sigma A. Q is sigma into A. So A get cancels. So finally, we will get E is equal to sigma divided by 2 epsilon naught. E is equal to sigma divided by 2 epsilon naught. So this is a very important mathematical expression. This is an expression for electric intensity at a point due to a uniformly charged infinite plane sheet. So this is the expression for electric intensity at a point due to uniformly charged infinite plane sheet. So electric field at a point due to uniformly charged infinite plane sheet does not depend on the distance from observation point to the sheet. Okay. Suppose the point is very close to the sheet, the electric field is sigma divided by 2 epsilon naught. So suppose the point P is far away from the sheet. In that case, also the electric field is same. E is equal to sigma divided by 2 epsilon naught. So here the electric field, electric intensity does not depends on the distance from observation point to the plane sheet. Okay, so this is the second application of Gauss's law. The next one. So this is the third application of Gauss's law, and this is also very important for 5 mark. That is derivation of expression for electric intensity at a point due to uniformly charged thin spherical shell. Derivation of expression for electric intensity at a point outside the uniformly charged thin spherical shell. Okay, this is the last very important 5 mark derivation. Okay, first let us consider a thin spherical shell. This is a thin spherical shell. Suppose if the electrons are removed from the thin spherical shell, what happens? The spherical shell gets positively charged. So what amount of electric field produces around this positively charged spherical shell? So we have to calculate that electric field, electric intensity. Okay, now let us consider O is the center of the spherical shell. This is the point O, that is the center of the spherical shell. Now we can choose the observation point P. At that point, actually, we have to calculate the electric intensity, electric field that is produced by uniformly charged thin spherical shell. Now we choose an imaginary Gaussian cylinder. This is imaginary Gaussian cylinder. What is this? Imaginary Gaussian cylinder. Gaussian surface. Imaginary Gaussian surface. So the distance from the observation point P to O, let us consider that is small r. Small r is the distance from the observation point P to the center of the spherical shell, and let us consider capital R, that is the radius of thin spherical shell. After that, we can choose a small surface, that is ds, on the Gaussian surface. What is the direction of ds vector? So normal is always directed outwards. Normal means the imaginary perpendicular to the given surface directed outwards. So here ds vector is directed radially outwards. So this is the direction of the normal, direction of ds vector. And unit positive test charge plus q naught is placed at the observation point P. Plus q naught is placed at the observation point P. So what happens due to this positively charged sphere, flex Q naught will experiences repulsive force that is directed away from the uniformly charged spherical shell, that is directed radially outwards. So here ds vector is radially outwards. Even the electric field, electric intensity is also directed radially outwards. So this is having the surface charge density. Let us consider that is sigma is equal to Q divided by S. S means the total surface area of the spherical shell, that is total surface area 4 pi capital square. So the charge enclosed by the Gaussian sphere, that is sigma into 4 pi capital square. Call this as equation number 1. Okay. So after that, we have to calculate the electric flux through this small surface, that is ds. So electric flux through a small surface ds, that is d phi e, is equal to E vector dot ds vector. Electric flux, small electric flux is measured by taking the dot product of electric intensity at that point and the small surface area, that is ds vector. This is a small electric flux through this small surface ds. D phi is equal to E vector dot ds vector. But we want the total electric flux through the entire Gaussian sphere. So what we have to do? Just integrate the equation on both sides. So after applying the integration, we will get integration of d phi, that is equal to integration of E vector dot ds vector. Integration of d phi e, that is phi. Phi is the total electric flux through the entire Gaussian sphere. So integration of dot product of two vectors, that is given by the product of magnitude of two vectors, that is EDS, and cosine of the angle between two vectors. Both are directed radially outwards, both are parallel. So what is the angle in between them? That is 0. So EDS cos 0. So phi E is equal to, here E means the magnitude of electric intensity. So the magnitude of electric intensity at any point on the Gaussian sphere, that is same, because the observation points on the Gaussian sphere, those points are equidistant from the center. The magnitude of electric intensity at any point in the Gaussian sphere, that is same. That is actually 1 divided by 4 pi epsilon naught Q divided by R square. So E is constant, so that is taken as outside. So E integration of ds cos 0 is 1. So phi E is equal to E into integration of ds is S. What is the meaning of S? S means the total surface area. Total surface area is 4 pi r square. Now call this as equation number 2. Now apply the Gauss's law. So according to Gauss's law, the total electric flux through any closed surface, is 1 over epsilon naught times the net charge enclosed by the closed surface. Now call this as equation number 2. Now call this as equation number 3. Now the equation 2 and equation 3. So then we will get, what is the value of phi? Phi is E into 4 pi r square. E into 4 pi r square, that is equal to Q divided by epsilon naught. After that, E is equal to 1 divided by 4 pi epsilon naught. 4 pi epsilon naught into Q divided by R square, right? After simplification, we will get E is equal to 1 divided by 4 pi epsilon naught into R square. 1 divided by 4 pi epsilon naught Q divided by R square. So this is the mathematical expression for electric intensity at a point outside the uniformly charged thin spherical shell. This is in terms of charge, in terms of the surface charge density. So in terms of sigma, this is very important point. In terms of sigma, what is the value of Q? Q is sigma into 4 pi R square. Now the equation 4 becomes here. Equation 4 becomes E is equal to 1 divided by 4 pi epsilon naught. The value of Q is sigma into 4 pi R square. Sigma into 4 pi capital R square divided by small r square. So here 4 pi get cancels. So finally we will get E is equal to sigma divided by epsilon naught into capital R square divided by small r square. Right? So after that in vector form. So what is the expression for electric field? E vector is equal to 1 divided by 4 pi epsilon naught Q divided by R square into R cap. So R cap, that is the unit vector, indicates the direction of electric intensity at point P, that is directed radially outwards. So R cap is a unit vector directed radially outwards. And this is a mathematical expression for electric intensity at a point outside the uniformly charged thin spherical shell. And this is in vector form. And this is same as that of electric intensity at a point due to the isolated positive point charge. Actually here, the n-type charge on the spherical shell. The n-type charge, that is plus Q. That is the n-type charge on the spherical shell. Actually, that is assumed to be concentrated at its center. The n-type charge on the spherical shell, that is concentrate, that is actually concentrate at its center. So then we will get electric intensity at P due to plus Q is 1 divided by 4 pi epsilon naught Q divided by R square. It's same as that of electric intensity at a point due to isolated positive point charge. Okay, the next case, that is, suppose if the electric intensity on the spherical shell. So the observation point P lies on the spherical shell. So in that case, actually the electric field strength is much stronger. Suppose if the second case, if P lies on the surface, P lies on the surface, P lies on the surface. So what is the value of small r? Small r is equal to the radius of this spherical shell. Small r is equal to capital R. Okay, so then we will get the expression E is equal to 1 divided by 4 pi epsilon naught Q divided by capital R square. So this is the expression for electric intensity at a point on the spherical shell. So in terms of sigma, in terms of sigma, so E is equal to 1 divided by 4 pi epsilon naught. What is the value of Q? Q is sigma into 4 pi capital R square divided by capital R square, 4 pi cancels. This is just E is equal to sigma divided by epsilon naught. So this is the mathematical expression for electric intensity at a point on the uniformly charged thin spherical shell, in terms of surface charge density. Okay, suppose observation point P lies inside the spherical shell. Observation point P lies inside the spherical shell. Now we can choose the Gaussian sphere. Actually, this Gaussian sphere encloses zero charge. Suppose if the charge Q is 0, what is the value of electric field? Electric field is 0. That means inside the electric field inside the uniformly charged thin spherical shell is 0. So this is also very important. This is case number C. Suppose if P lies inside the spherical shell, so in that case, the electric field strength is 0. So electric field inside the uniformly charged thin spherical shell, that is equal to 0. Okay, how does the electric field varies with the distance? So that is also very important. So let us consider a small graph here. This is x-axis, this one is y-axis. This is a uniformly charged, this is the center of the spherical shell. This is uniformly charged thin spherical shell. So what is the electric field inside the uniformly charged thin spherical shell? Electric field inside the thin spherical shell is 0. Actually, this is the graph of E versus R. E versus R. So here the electric field is 0. Up to the surface, the electric field is 0. Here the electric field E is equal to 0. Inside, the electric field is 0. On the surface, the electric field is maximum. At this point, on the surface, the electric field strength is maximum. That is, E is equal to 1 divided by 4 pi epsilon naught Q divided by capital R. So, as the distance from the spherical shell gradually increases, suppose if the distance from P to spherical shell, observation point P to spherical shell, that is gradually increases. Small r is gradually increases. Then the electric field strength is gradually decreases. So this curve touches the x-axis at infinity. So this curve touches the x-axis at infinity. What is the electric field strength at infinite distance from the uniformly charged thin spherical shell? That is equal to 0. So this is a rectangular hyperbola, and this curve indicates E is inversely proportional to the square of the distance from the observation point to uniformly charged thin spherical shell. Okay, thank you.